So now we are ready to define the problem. We know what a tree is and we have recalled or refreshed our concepts about trees. So the distance based phylogeny problem goes in this way. You want to construct an evolutionary tree from a distance matrix. Input will be a distance matrix and the output is an unrooted tree fitting this distance matrix. Later on we will think about how we may want to root this tree, but for now let us just say that we want to only look at unrooted tree that is consistent with this distance matrix. Okay, we want this is a reconstruction problem like I said before, or a realization problem. We want to reconstruct or realize a tree, an unrooted tree that is consistent with the distances in this distance matrix, that will fit this distance matrix. Okay, but we have seen before that terms like fitting and consistent are very loose terms. So this is not a proper computational problem yet. So we need to clarify what we mean by fitting, right, and then let us just try to define what fitting is in very clear computational terms, so that any computer scientist who does not know anything about biology or distance matrices would be, or sequences, would be able to understand this problem and lend forward her or his ideas on how to solve this problem. Okay. We want to fit a tree to a matrix. That essentially means that you want to come up with an unrooted tree such that all the distances that the tree implies, the tree distance, right, the tree will have these nodes and edges, and the edges will have these weights. Okay. You want to make sure that you come up with an unrooted tree with a set of nodes and edges, right, with edge weights, and the leaves are all the species that are the species of interest. So this chimp, human, seal and whale, such that the distance of the path, because it is a tree there is only one path and only one path between any pair of species or leaves, right, or any pair of nodes in the tree for that matter. So you look at the distance between them. In this case chimp to whale would be 1 plus 3 plus 0, that will be 4 and then you see if that matches the distance matrix that you have with you. Okay. So that is what is called fitting a tree to a matrix. So chimp to human in this is 1 plus 2 is 3, so that is 3 in the distance matrix as well. Chimp to seal is 1 plus 3 plus 2, which is 6, it again matches what is in the distance matrix. Chimp to whale we have already seen is 4, the tree distance is 4 and the distance matrix that is provided as input is also 4. So this is the input distance matrix that is coming from the sequence alignment and the sequences, right, and this is your output or the desired output, which is a tree whose distances match the input distance matrix. Okay. So chimp to whale is also matching, human to seal is 2 plus 3 plus 2, which is 7, so that is also matching. Human to human to seal is 7, human to whale is 2 plus 3 plus 0 5, that is also matching. Finally seal to whale is 2 plus 0, which is also matching. Okay. So this is a tree which fits this matrix, this distance matrix. Okay. A tree that fits this distance matrix, because the distance between every pair of species or leaves in this tree is exactly matching the distance that is provided as input to us in this distance matrix. Now let us come back to the distance based phylogeny. We want to construct an evolutionary tree from a distance matrix. The input is a distance matrix coming from a sequence alignment, for instance, and you want the output to be an unrooted tree fitting this distance matrix. Okay. So you want by fitting, now we have clarified what it is. So we have removed the quotes. You want the tree distance or the distance between every pair of species implied by the tree, which is this small d, to match, well, let us call this capital D, to be equal or same as the capital D. Okay. Now the question again is this problem well defined? We have clarified what fitting is. Can you stop and see if this problem is well defined? Specifically, will there always be one tree that will fit this distance matrix, or can there be multiple trees that will fit this distance matrix, right? Is there any ambiguity still in the problem? We are saying the unrooted tree fitting this distance matrix? Is it always only one unrooted tree, or can there be many unrooted trees fitting a particular distance matrix D, right? That is one issue. There may be other issues also. Let us just look at it, right. And also another thing is, the one thing I said is ambiguity, right. Can there be more than one trees? More than one solution. Another thing is, for every distance matrix, will there even be such a tree, right? Will such a solution even exist, right? Can there be more than one solution is the ambiguity. Another thing is existence. Is there a tree for every D, every possible D that is provided, a distance matrix that is provided as an input, right. So, here is one distance matrix, and the exercise is to try to fit a tree to the following matrix. Okay, so let us just try this, right. So, you have I and J and K and L, those are the 4 species. So, you have I and J, and it seems to me that I and J are at a distance 3, K and L are at a distance 2. So, maybe I will just put this as this 1 and 1, maybe this is 1 and 2, right. And then I and K is 4. So, maybe this has to be 2. So, then I to J is 3, this is okay. I to K is 4, because this 1 plus 2 plus 1 is 4. So, that is okay. I to L is 3, but here I to L is 1 plus 2 plus 1, which is 4. So, this one is not equal to 4. Here we get this D I L is 4, but this capital D I L is 3. Okay. So, this D I L is not equal to D I L, right. So, capital D I L not equal to small d I L. Let us look at J to K is 4, J to K is also 5 here. So, this is also not equal to 5, in the tree it is 5, right. And then J to L is 5, J to L is 2 plus 2 plus 4 is 5. So, this is okay. Finally, K to L is 2, so K to L is 2 is also okay. There are 2 entries which we were not able to match, right. All the other entries we are able to match. We can try fudging things around. This is just one example tree, maybe there is some other tree which will match all the entries. So, we have to match 1, 2, 3, 4, 5, 6 entries, right. This is a symmetric matrix and this particular tree only matches 4 out of the 6 entries. Okay. So, we will come back to this matrix later on, whether there are some other trees that will fit this matrix. We will leave it as a mystery for now, okay. And then let us start around this, let us start thinking about the existence of a tree fitting a particular distance matrix, okay. So, there may be distance matrices that will not fit any tree, right, and in that case let us just say that an additive matrix is one such that an additive matrix is a distance matrix such that there exists at least one unrooted tree fitting it, right. There exists an unrooted tree fitting it, okay. If you have a distance matrix and there is an unrooted tree that fits this distance matrix, then that is called an additive matrix. If there is a distance matrix and no tree, however hard you try and you try all possible trees, all possible edge weights and so on, and none of that will fit this particular distance matrix, then those are distance matrices are called non-additive distance matrices, okay. And like I said, it is not just whether a tree exists or not, but sometimes if a tree exists there may be multiple trees that fit a distance matrix, right. So, here is an example where this is the additive. So, this distance matrix is additive distance matrix, because we know that this tree and the tree distance, this implies D, right, Dij over all I and j is going to be equal to the Dij that is shown here over all Ij, right. So, this is an additive distance matrix and this is one tree that will match or fit this additive distance matrix. But you can also come up with other trees. So, for instance, I can split this 2 and 2 edges into one internal node, and I can make it 1 and 1 and 1.5 and 0.5, right. So, which tree is better in your, I mean in our situations we do not like branches which are I mean kind of paths which are non branching, right. So, these are just, it looks like this node is just an unnecessary node. In those cases I would actually prefer a simpler tree which is looking like this, right. So, a tree with no degree 2 internal nodes, right. So, this is a node with degree equal to 2, right. But in all the other cases this is degree 1, all the leaves are degree 1, and this is degree 3, right, this is degree 3. Similarly, here it is degree 3, degree 1 and so on. Okay. I do not want paths in this in my phylogenetic tree where the paths are not branching at all, right, that all the nodes in the path except for the ending nodes are all of degree 2, right. So, I want to simplify it and then get rid of those nodes. Okay. Like I said, these are the degree 2 cases, and we want a simple tree which I prefer, right, and then in the community also prefers. We do not want these unnecessarily complicated trees shown in the bottom, we want the simpler tree shown in the top, right. And this simple tree actually can be formally defined by saying that a tree with no nodes of degree 2 is called a simple tree, right. Simple enough. So, because then these kinds of paths will be removed and then this will be replaced with something like this. Okay. So, this is the bottom is not a simple tree, the top is a simple tree. Okay. And this, once you have this, then there is a theorem which says that degree 2 nodes are the ones that create the trouble. Okay. If you remove the degree 2 nodes and you only allow degree 1 or other higher degree nodes, right, degree 1 or 3 nodes, right, then there is a unique simple tree fitting an additive matrix. Okay. There is always a unique tree that fits an additive matrix. So, we do not have to worry about ambiguity in terms of, okay, this is an additive distance matrix, can there be more than one simple tree fitting it, right. No, there will only be a unique simple tree fitting it. We will not prove this theorem, but we will take it on faith and go back to our formulation finally, right. So, you want to construct an evolutionary tree from a distance matrix. You have a input is a distance matrix, your output is the simple tree fitting this distance matrix if this matrix is additive. Okay. This addresses both of the issues on the existence. If this matrix is additive, then only I can output a tree, and also uniqueness, because I am asking only for a simple tree, there cannot be more than one tree fitting the additive matrix. Okay. So, now we have a very concrete computational problem that we have iteratively formulated over the last several slides. Okay. Once we have a concrete computational problem, there is no ambiguity in the problem, the solution always exists if the matrix is additive. So, all of that has been made clear. Now, let us go ahead and see if we can come up with an algorithm for this distance based phylogeny reconstruction. Okay. One way to understand this is this kind of go for the smallest distance first, right. I can go into this distance matrix, I can look at the smallest distance which is 2, and then I can make them to be the closest neighbors, right. So, seal and whale I am going to make them closest neighbors, the rest of the tree I have not figured out yet. So, but the seal and whale I am going to make them have the common parent. Okay. This construct is also called a cherry. It looks like a cherry bunch of cherry fruits from a common all bunched together, right. So, this internal node is the place that holds this bunch together, and then these two cherry fruits are there. So, you have now picked a cherry, they also call it as finding a cherry or picking a cherry. So, the seal and whale are the closest ones in terms of the lowest distance, and you make them a cherry. And those with the smallest distance, smallest pairwise distance, those you share the parent and you construct the structure. Okay. Now, there is a theorem again which is something that you just spend a little bit of time and you will be able to prove it yourself, is every simple tree, meaning a tree with degree 1 or degree 3, right, or higher degrees, you are not looking at degree 2 nodes. Okay. So, every simple tree with at least 2 nodes, okay, it is a non-trivial tree, you have at least 2 nodes, has at least one pair of neighboring leaves. Okay. So, let us just look at some examples. So, here is a seal and a whale, right, and let me just show some other examples also. So, here is a tree, right, here is one cherry, right, here is another cherry, here is another cherry, and then so if these species are called S1, S2, S3, S2, S3 is one cherry, S1, S2 is another cherry, and S1, S3 also forms a third cherry, right. Here this may be S4, S5, S4, S5 is a cherry, S6 is not forming a cherry. Okay. So, this is one example. Another example could be I am trying to draw a tree where I can and then this node is degree 2. So, I need to do some things like this, right. In fact, you can even show that if you have at least 3 nodes, for instance, right. So, you have or at least yeah, at least 3 nodes, for instance, you can show that there are at least 2 cherries. Okay. Let us say the nodes are in this way, then here there are 3 cherries, right. So, these are just examples, but you can also prove that every simple tree with at least 2 nodes has at least one pair of neighboring leaves, and that means at least one cherry. Okay. So, let us just go ahead and because we know that there is always one cherry, let us just go ahead and pick that cherry, right, figure out the cherry. But once you have this 2, we need to figure out what are these values here. Let us not put them yet, right, but how can we compute these unknown distances, and these distances will depend on the distance of seal and whale to the other organisms in the tree, right. So, without looking at other entries of this distance matrix, we will not be able to fill these things. We just know that this plus this will be equal to 2, right, but we need some other information to figure it out. But think how we can do that. Like I said, we know that this question mark and this question mark has to add up to 2, but then to figure out is it 1 1 or 2 0 or 0 2 or how you split it up, you basically use this formula. And another way to see this formula is simply that you have this I here and j here, and you look at some other species k somewhere else in the tree, right, and you want to know what is, and this is your m that we had looked at, this internal node that is the parent of I and j, right, and you want to know what is di to m, right. In order to do di to m, so I just go from di to k, right, this is di to k, right, and then I subtract out dj to k, right. So, then this part is subtracted out, right. So, j to m is being subtracted, right. So, I need to add now dj to I, so that the subtracted one is again added back, right. So, this I am going to put as an arrow mark like this, right. I take this d, the first one which is d I to k, I subtract out d k to j, but then I have subtracted more than what I need, I need to add back d m to j. So, to do that I add d j to I, which will add back d m to j, but also additionally add m to I, and so m to I is added once here and then finally another time more. So, I have to divide it by 2. Okay. I hope that part is clear. I want you to take a moment to think about this very intuitive formula, okay, k to be this chimp. Okay. So, this is k, seal is I, whale is j. Okay. So, using this formula, so this d I to m is what is this, right. So, this is going to be d seal to, right, d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I to m is what is this, right. So, this is going to be d I chimp minus d whale to chimp plus d seal to whale divided by 2, right. So, exactly writing this formula, but for I j k using these I j k. Okay. So, then this is going to be d seal to chimp is going to be 6, whale to chimp is going to be 4, seal to whale we know is 2 already, that was this 2 divided by 2, which will be 2, right. So, this question mark is going to be 2 because this is 2 and this has to be 0, okay, because both of them has to add up to 2. Okay. I hope that part is clear, and this also gives you the distance from M to chimp, which is 4, because we know that seal to chimp is going to be 6 or whale to chimp is also going to be 4. So, that is also consistent with this distance. Okay. Now, you can do that similar thing. So, you can also say if I use humans, right. So, then what is M to humans, and I can use the same thing and say that human to seal is 7, human to whale is 5. So, this got to be 5. Okay. So, now I have decomposed this problem. If seal and whale are indeed cherries, right, if our decision there was true that seal and whale are indeed closer together and then they share the common parents, then we have already constructed this part of the tree. So, we can recurse on this, we can replace it all with another node M prime, right, and then we only have to then do the problem on a smaller number of species, which is M prime, chimp and human, one less, right. Previously we had 4, but now seal and whale are taken care of, both of them can be removed and this internal node can be kept as is. Actually I can call it M also, right, and then now I have a new distance matrix where seal and whale has been removed and the new node M has been added, and from M I know the distance to every other node, it is 4 to chimp, 5 to humans and 0 to M itself. So, from a 4 cross 4 distance matrix D, if I have picked a cherry correctly, I have reduced to a 3 cross 3 distance matrix D. This is over all the 4 species, this is over 2 species and an internal node M. Okay. So, that is what this looks like. So, this is one idea for the distance based phylogeny. So, now you have a 3 cross 3 distance matrix, right, and then you choose the smallest entry in the distance matrix, which is chimp and human, and you make them as the cherry, right. You pick that cherry and then you basically have another node A, which is the common neighbor of that or common parent of that set of 2 species, okay, or set of 2 nodes. That is what we are going to do. So, we have made chimp and human as the cherry, and then A is the common neighbor for chimp and human, right, the common parent, and again we have the same issue that we need to figure out this length question mark and question mark, which will add up and give you the value 3, right, and we can apply the same formula as before, right. I will say it again. So, I have D chimp to M, that will be this first line, then I have to subtract D M to human, that will be this this slanted line, this striked out line, that is the one that we are subtracting, but that is subtracting more than what we need. So, you have to add back D human to chimp, but then that is adding this both this normal line here and also this arrowed line here. So, we will have to divide all of this by 2 to get D or this little d chimp comma A. So, this is going to be D chimp comma M is going to be, we know this matrix. So, D chimp comma M is 4, D M comma human is 5 plus D human comma chimp is 3, we know, divided by 2, which is equal to 1. Okay. So, this question mark is going to be equal to 1, because of that this other question mark will be 2. So, both of them add up to 3, right. This is exactly shown here. This will be 1 and so this will be 2, and then based on that this final link can be added, which will be 3. Okay. And then you can kind of go back from this 3 cross 3 distance matrix, and you can add back seal and veil and remove the M, and you will get a 4 cross 4 distance matrix, and you get the full tree which fits that distance matrix. Okay. So, this idea for distance based phylogeny is this concept of repeating these two procedures: pick a cherry, right, reduce the dimensions of the matrix, pick a cherry and figure its branch lengths, and then you reduce the dimension of the matrix by collapsing the query into the common neighbor node, right. So, this seal and veil, you collapse that query into M and you remove seal and veil, so that you got a smaller distance matrix. You can continuously recurse on it, even if it is not 4 species, but hundreds of species, this program would still work as long as you pick a cherry correctly, right. The cherry that you pick is correct every time. Okay. So, that we still have to formally show or see if there is any issue with that. Okay. And we would like to understand how it will work for a distance matrix like this. So, this is an exercise break. Okay. Let us just go ahead and apply this. Okay. And the reason that this particular matrix is given as an exercise break is you will see that the concept of picking the cherry may not work all the time, right, the way that you pick the smallest entry, right. So, let us look at this concept of taking this idea and then converting it into an idea called the additive phylogeny that works for all matrices, and also for matrices that it does not work, we need to get some understanding, or the algorithm should say that for this matrix there is going to be some trouble, right. Okay. So, it looks like we have a good idea now that we will keep on picking a cherry, and then we will figure out the branch lengths of the cherry, and then we will keep on recursing on that idea. We will remove the cherry and then keep only the internal node, the common parent of the cherry, and then keep recursing it until we get all the cherries and all the proper edge weights of the tree that we are constructing. Okay. But this algorithm will only work if we pick the right cherry every time. Okay. And the strategy or the idea we have used here is very intuitive, that you look at the distance matrix, and then whichever entry is the smallest in this distance matrix, it is this entry 2, and then you say that that pair of species forms the cherry. Okay. But this may not always be true. Okay. Let us just look at an example. So, this is one matrix where that will not be true. We will see it a bit clearly later on, but let us also look at another matrix, a very simple matrix and a tree. Okay. You have a tree where you have I and j and k and l. Okay. And I can assign edge weights in this tree, right, so that the closest the cherries in the tree is not going to be the smallest distance. Okay. So, maybe I can put 100 here, I can also put 100 here, and I can put every other edge 1, right. So, now if the distance matrix that this tree fits is the following, right, you have I j k l, all these entries are 0, this is a symmetric matrix, so I am not going to draw the bottom one. So, now you have I j k l, you have L to k is 101, so you have L to k is 101, you have I to j is 101, right, and you have k to j is 3, k to j is 3. Okay. You have I to k is 102, I to k is 102, you have I to l is this one, right, that is 201. What is j to l? That is 102. Right. You have here where I have made these edges to be really large weights, and so among these pairs j and k are the ones with the smallest distance of 3, right, but then they are not cherries, right. So, j is a cherry with I and not with k, similarly k is a cherry with L and not with j, right. So, if we just look at the distance matrix, which is what will be provided as an input to us, we will not know the true tree. So, this is hidden from us initially, right, we are trying to reconstruct this, this is what is shown to us, and then using this we may wrongly conclude that j and k with a distance of 3 is going to be cherry, but it is not the case here. So, j and k are actually in two other extremes, they are forming cherries with I and L respectively and not with each other, right. So, if the algorithm goes forward assuming that j and k is a cherry, then it is going to make the wrong decisions and we are not going to get this right tree with us. Okay. On the other hand, if we are able to find the right cherries from here k and L or I and j, then we will be able to use the same algorithm and that should work. Okay. And this is another distance matrix, this is an additive distance matrix, okay, where the smallest entry is this j and k, right, but j and k will not be cherries in the tree that fits this additive distance matrix. Okay. Let us just look at that. So, here is the our algorithm, and applied to this distance matrix you would not have obtained a tree that fits this distance matrix, because our algorithm or this idea of choosing the smallest entry as our cherry is wrong for this matrix. In this particular case this is the correct tree that fits this distance matrix D, and you can see here that this j and k of 12 is not actually a cherry, they are on the other extremes, they are cherries with other nodes, okay, they are not cherries with each other. Okay. Then again you have this concept, previously we had this other example where we had 100 here, 100 here, 1 1 1 here. So, these two edges were larger than the other 3 edges. Here also you can see here that there is 11 is larger than the other edges and 7 is also larger than the weights of the other edges. Because of this arrangement or configuration, the j and k in the tree they are not cherries, but then their distance will be the smallest among all pairwise distances. Okay. I hope you get this class of distance matrices which will not reveal the correct tree if you go with the algorithm's idea of picking the cherry as the entry dij with the minimum value. Okay. This idea is wrong. Okay. We need to have a better idea, the correct way of choosing the cherries. Okay. That is what we will do in an algorithm called neighbor joining. Okay. We will find the correct cherries and then we will proceed along with that. But before we go there, can we look at the problem slightly differently, and that is what we will do in terms of something called the additive phylogeny. Okay. That is the first algorithm we will see for the problem, a first correct algorithm for the problem. Okay. The one that we have seen so far in terms of choosing the smallest entry is not the correct algorithm.